Hey folks, this is AP Chemistry, and you're here with Miss Gray for Falcon High School AP Chem. We're in Unit 9, Colligative Properties. So basically, we're going to look at properties of solutions. So first, let's talk about what solutions are. Solutions are formed when one substance disperses evenly throughout another. So it's the ultimate type of homogeneous mixture where you cannot distinguish the one particle from the other. The solutions for something to actually dissolve is going to involve interactions of intermolecular forces. That's what Unit 8 was all about, right? IMFs? And so there's a reason we did that unit first, so that we could understand how they work in solutions. You see, a solution will form when the attractive forces, the attractive intermolecular forces between solute and solvent particles, are equivalent in magnitude to those that exist between solute and solute particles. Equivalent. Okay, see, I can't even spell equivalent. In magnitude to those that exist between the solute attraction for the solute or the solvent's attraction for the solvent. Let me show you what I'm talking about. With oil and water, for instance, there's an attraction for one water molecule to another through hydrogen bonding, right? Through the partial positive charge on the hydrogen end and the partial negative charge on the oxygen end. So then, because of that attraction, those particles will move closer together, and these other particles move closer together because of that electrostatic force. When they do, though, it squishes the oil particles up out of the way. There's no attraction that the water has for those oil particles, and the oil particles don't have any attraction for the water. So as the water gets closer and closer together, the oil, being less dense, gets pushed out of the way so that the water can get closer to its own self. So that's why oil and water don't mix. You see, the nonpolar substance got pushed away, and if it were moving faster, it might even break through the attractive forces. And so solubility is really a balance between speed and attraction. Things that are moving faster can't be held by that attractive force quite so well. And the more similar the strengths of their dipoles, the more likely two compounds are to mix. The process of dissolving starts with solvation. It's a generic term for any solvent, solvation, wow, that happens when a solute particle gets completely surrounded by solvent molecules. This is an important step in the process of dissolving something, is to surround it with the solvent. And if we're specifically talking about dissolving things in water, then this process is known as hydration, where the solvation that occurs is occurring when the solvent is water. So we call that hydration. For any solution to form, the saying is like must dissolve like. In other words, polar substances dissolve in polar solvents, and nonpolar substances dissolve in nonpolar solvents. That's all there is to it. Like dissolves like. Oh wow, and see, there you go. Oil doesn't dissolve in water, and we already saw that. So let's look at a special molecule called soap. You see, soap has this end that's known as, soap has this end of the molecule known as the hydrophobic end. This is the nonpolar site. It's just a long chain of hydrocarbons that have no polarity. Because of the geometry, it simply cancels out every polar bond in there. But then there's this end that's called hydrophilic because of the charges on the phosphate here. These phosphate charges is a 3- charge, right? That's going to have a strong attraction for the polar bond, for the polar molecule in water. So we have a hydrophilic or water-loving end, and then we had this hydrophobic or water-fearing end of the molecule. And so soap has unique properties that allow it to dissolve oil particles. So let's have a look at some grease. That's a big drop of grease. So suppose we have a drop of grease in the water, And grease is, of course, a nonpolar molecule. But the water is polar. So we've got a problem. How are you going to wash grease away when it won't dissolve in the water that you're trying to clean it up with? We use soap. Soap allows you to dissolve the nonpolar molecule. Soap allows you to dissolve a nonpolar molecule in a polar substance. So let's see how this works. So first of all, we take our droplet of grease and we take all of our hydrophobic ends and they dissolve in the part that is grease. So all these long chain hydrocarbons, they're going to stay inside the grease because they're hiding out from the water. See, the water's out here? They don't like the water. So if they stay here embedded in the grease, then they don't have to touch the water. But then the hydrophilic end, oh dear, skipping ahead. The hydrophilic end does dissolve in water. This is the end of the molecule, remember, that has the phosphate on it? And so that phosphate end is attracted to the water, and because of this, it makes a soap bubble, where they all sort of line up. And a soap bubble has a lot in common with the cell membrane. Remember, you may have studied in biology the phospholipid bilayer. Phospholipids are like these particles, where there's a hydrophobic end and a hydrophilic end. Phospholipid comes from the term phosphate with fat. And so these chemical properties that we're studying in chemistry are really the driving force behind everything you had to learn in biology. That's why it's called the fundamental science. So we have these water molecules that can now surround and dissolve the grease because the water is attracted to the phosphate end of the soap. We have our little soap bubbles surrounding the particles of grease. And so this helps to get the grease out of your way, and you can actually wash it off and wash it out of the way because it's dissolvable now. Wow, that was it for that first podcast. The end snuck up on me. So I'll see you guys in class, and we'll be practicing more with these concepts.